Hello everyone. In this video, we are going to talk about vision-based place recognition in robotics using bag of features. So what is place recognition? It means being able to recognize a place that you have seen earlier, right? So if your robot is just going around some neighborhood, some campus, anywhere, a lab, and capturing pictures, and you can do this manually. You don't even have to necessarily autonomously move the robot. And it comes back, and now you let the robot go again and see if the robot can recognize any of those previous places. This is place recognition. This is one of the fundamental tasks for mobile robots. Why? Because using that, you can recognize your location. If you record the location of the robots when you took those pictures, if you can recognize one of them again and say, hey, that was this specific feature or building or something, and I took that when I was at position X and Y, then guess what? You can localize yourself. And you can do that in SLAM, which is one of our future topics, to do a loop closure. And loop closure in SLAM is exactly that you visit another place and you do the loop closure. We'll talk about it. And so on. Or if there are dynamic environments, if you want to detect any changes, this place recognition for SLAMs that are vision based, like vSLAMs, this is a very, very fundamental task. Now, place recognition can either be done using global representations or local representations. So, what is that? Global representations are techniques that you represent the entire image with some kind of representation. Like what? Like, for instance, you use the histograms of something in the image. You use fingerprints. You use PCA, right? To basically reduce the dimensions, principal component analysis. You use some Fourier transform. Most of the time you use a kind of domain transform version of the image to reduce the dimensions. And that whole image is represented by, let's say, a histogram or some Fourier series or something like that. Or no, you detect salient regions of the image, interest points, features like SIFT points, surf points, or anything, and then you represent the image by those local features. Okay? In this video, we are going to focus on the local representation using bag of features. In the next video, we are going to look at the global representations using histograms and fingerprints using HOG. So stay tuned for two videos back to back. And the material here, as many of our previous videos, is again coming from the amazing book by Sigward, Noorbakhsh, and Escaramuza, Introduction to Autonomous Mobile Robots. And the picture I have here is from the MathWork website. This is a very good picture. I decided to go with that because there are some pictures in this book too, but this picture is much, much better about the bag of features. So what is a bag of features? Basically, bag of features means you represent the image in terms of some interest points, some salient points only. So instead of me showing an entire image, I'm basically focusing on some salient points, right? So let's say, for instance, here is an image, and in this image, the interesting things are, for instance, some pattern on the door or some on the window or something, right? Or let's say if I'm showing you a hat or something, maybe some of these edges, some of these patterns on the hat or anything like that, the salient features is all I use to represent the image. Now, one thing important about it is, since you represent the image by this collection or bag of these features, basically, you're ignoring spatial arrangement, okay? And so you see how many of these features are present in the image and with what frequency. Okay, so when you use these, you're losing. It's like you're putting some marbles in a bag, and so the order of them is now lost. They are just mixed in a bag. But I'll talk about it later. When you want to do place recognition and you use bag of features for initial search within the database, you can later reinforce back the special information. So what do we do here? Your robot goes ahead and captures images back to back and extract local features using any kind of feature detector and then describes them. So, for instance, we use surf feature detectors and surf feature descriptors, and we get like 128 dimensional feature SIFT feature descriptor, right? Or surf or anything like that. So now that we detected these points and described them with these high dimensional vectors, let's say, then one thing we do, we convert these higher dimension descriptors into basically 1D representation of them, and those 1D, those lower dimension representation of these large vectors is what we call a visual word. Okay, so visual word, like for instance a single integer. So we assign to one set of a bunch of 128 dimensional SIFT features number 1 to another set, number 2, number 3, number 4, and so on. And then in that space, we can also do a clustering, which we're going to talk about it. We're going to do k-means clustering. And so basically, each part of that space now belongs to one set of or one group of these features. Okay. So if you hear the word the terminology visual word is like a 1D representation of these features or feature vectors that are very high dimensional typically. So what are the steps to create a bag of features? The step is this. First, as I said, detect the key points, detect the salient points. You can use SIFT, SURF, ORB, anything like that. And they could be corner points, blobs, anything, any region like with high texture variation, anything like that. Now describe them. Create a vector that describes the surrounding of these points. As I said, SIFT has a vector with 128 numbers, okay, which describes the local gradient distribution. Now that you detected them and described them, now it is time to what we call construct a vocabulary. What is that? So now with all of these descriptors that you got from all of my training set, and training set is all of the images that your robot collected, now when you collect them, now you cluster them using k-means clustering to a set of k visual words. Let's look at this picture. This picture, as I said, I got it from MathWork website. This is a really good one. So look here, this is what we do. So what we do is we go ahead and we detect these, let's say, SIFT or SURF points. We describe them. Each one of these points has a large vector that describing it. And then from all of these images in your training set, in this case, you only see one, but let's say you have 1,000 images, 10,000 images of something. You bring all of these vectors in this higher dimension, and then you perform a k-means clustering with the number of clusters that is one of the parameters that you have to give to your algorithm. And you bring it down to, let's say, 50 clusters, 20 clusters, 100 clusters. This is a hyperparameter that you have to choose. So by clustering, you try to determine these boundaries of these clusters and, of course, their centroid. Okay. Now that you have k clusters, now for each one of their centroids, you assign a low dimensional vector, like for instance a single integer or something, and that low dimensional vector that represents each one of these centroids is what you call a visual words. Okay? So the purpose of them, as I said, is to convert the high dimensional data into a symbolic low dimensional, discrete low dimensional representation that allows you to do your job faster. Okay? Because imagine if you have thousands of these training images, and each one of them has lots and lots of these features, and each one of these features has a large vector describing the surrounding of it. Imagine how big this space going to be that you're doing the k-mean clustering. Okay, so you might do that, but once you do that, you want to now kind of bring the dimension down a little bit and kind of represent it in a nicer, kind of more compact form. And again, now each one of these is kind of corresponding to some kind of feature here, right? For instance, this cluster might correspond to some kind of corner like that. Or this cluster, maybe it corresponds to having both black and red band and red between the blacks inside some kind of yellow window, right? Or in this case, for instance, as I said, one of them could correspond to this feature of the window, one of them could correspond to some feature on the door, and so on. So they are the lower level representation of these, okay? Once you create that space, the centers, as I said, the centers of this cluster, the centroids, are going to be your visual vocabulary, okay? And each one of them corresponds to a visual word. Now, what? So you made your vocabulary and you went over each and every one of the images in the training set. Now it is time to get a query image. So you trained the system. Now your robot goes around again and finds or gives you a new image. Hey, right now I can see this image. Where am I? Okay, this is the time now for that new image that you find the, again, the interesting points, surf, sift, whatever, and you describe them again. You find the descriptors. Now with these descriptors that you have, and with those centroids and the results of k-mean clustering, you want to see these feature descriptors that you have is closer to which one of those centroids, okay? Is closer to which one of them. So here you do a, basically you might call it a voting system, okay? And one of the methods that you can do for it is called the inverted file method. So let me explain exactly how this inverted file method is working to find you the best match. So here, for simplicity, let's say you only have 10 images in the data sets, although of course most of the time you have way more than that. But let's say you have 10 images in the data set. So you create a voting array with 10 cells or 10 places, and then each one of them corresponds to one of the images in the data sets. Okay, so this is image 1, this is image 2, all the way to image n. And you have your new image, query image. You want to see this is closer to which one of these in the database. So what would you do? What you do is with this descriptor that you have for the query image, as I said, you create a descriptor. You can show it with vector x. Now you see this x is closer to which one of those centroids. And you can easily use the 2 norm here, the Euclidean norm, and find the minimum of that. So it finds that that descriptor is closer to which one of those centroids. Okay? And let's say in this case it's closer to this centroid, and that centroid is for basically, let's say it corresponds to this kind of feature or something. Now the question is, that kind of feature you can find in which one of these data sets? So if you go and search your data set, you'll find that, well, maybe image 1 had this feature in it. Maybe it had 1, maybe it had 10 in it, or as many as that feature was presented in image 1. So image 1 had 1 in it, image 2 maybe had 3 in it, image 5 had, like, for instance, 4 in it, image 10 had 8 in it of that feature. Okay? Yes? And then you repeat that for each one of these descriptors, correct? Because you don't have one point and you don't have one descriptor. You have lots of points, and for each one of them, there is a descriptor. So you do it for the first descriptor, you get a bunch of votes. For the second descriptor, you repeat the process, and again, the second descriptor, you compare it against these centroids, and you find maybe this time it's closer to this centroid, which corresponds to maybe this feature. Again, you look how many of the images in the database they have this feature, and how many of that feature is present in those images. So again, maybe this time this guy had 2, this guy had 6, this guy had 5, and so on, and this one had 1, correct? And then you repeat that for all of these features. So at the end of the day, each one of these images in the database, each one of them will get so many votes. So maybe in this case, this image number 10, based on all of these votes for different features, this guy gets the maximum vote, okay? Get this the maximum matching features. Well, then this is your best match. You say, hey, guess what? I found my best match. Not only it gives you the best match, this image, that's one of the good things about it, it can also give you the remaining images in the data set that are like second best place, third best place, and so on. So maybe this one has the second highest vote. So you see, this one is the best match, but this is the second best match. This is the third best match, and so on and so forth. Okay, so you can even come up with a probability now that with like 60%, this is the best match. With 40%, 20%, this is the best, 10%, this one. You can even use a softmax function and come up with probabilities here based on this total number of votes for each image. And you can come up again with chances, which is really great. So it gives you all of those probabilities as well, okay? And this method is quite a bit powerful. Okay, it's not the most powerful, but it's quite a bit one of the powerful methods. And of course, it could be only as good as these feature detectors and descriptors. So if your feature detectors and descriptors are doing a good job, and they are invariant to a bunch of different things, like for instance, rotation, scaling, translation, lighting changes, and so on, then probably your bag of features is going to be robust against those as well. Okay, so you need to pick some good ones here. And also another parameter under your control is the number of clusters, of course. And that is a hyperparameter that you can pick. Now, once you pick, let's say, your best, like out of these 1,000 images in your data set, you pick like the top 10 that are the top 10 best matches. If you want, you can do a final, what we call a final geometric verification. How do you do that? Now, you only pick those, let's say, top 10 or top 4 or top 3 in this case. So now, I only pick the top 3 images that are the best matches for this query image. What do I do now? Now I try to find a transformation between this query image and each one of them. Like what kind of transformation? It could be an affine transformation or a homography, okay? So I say, well, these two are quite a bit similar, but not exactly the same. Why? Maybe this image is a rotated version of that image, or it's a scaled version of the image, or a displaced version of the image, or anything. So I try to find an affine transformation or a homography that transform the query image to each one of them, okay? And then by ransack, I only keep the inliers, and then I will count which one of these will give me the maximum number of inliers. And if still the top one gives me the top also number of inliers, then that's definitely my option. But maybe this time when I do the transformation check and try to do a geometry, maybe this time the second one did not give me as many matching features, but this time it gives me a better match in terms of number of inliers after finding the transformation and ransack. Okay, so you can do a secondary check and a geometric transformation or verification to make sure that because you lost all of the spatial information, you want to see now that you're comparing the entire image against the entire image, not just features against features and descriptors against descriptors. Can I apply one single affine transformation to this and get this one? If I can, then that's my best match. Okay? So that is your secondary thing that you can do, and you can do a geometric verification. Now here I wrote a simple code. It doesn't do the geometric verification, but if you want, you can add that, of course. But here, from this great website, which is a bunch of pictures from Amsterdam, I downloaded a lot of images. Okay, it allows you to download lots and lots of images if you go to this great website, and you can use that. Let me show you. I guess it's this one. Yeah. So you go to this website and you go down, and then it is allowing you to download this zip folder which has lots of images, and you can use that to try your code. So here I have a folder that has like 200 images. The number of images in this zip folder is way more than 200, but just to make my code manageable, I only picked 200 of them. And then I have a query image, which is one of those 200 images, but I modified it. Okay, you'll see that I modified it and I cropped it and I moved it a little bit so they are not exactly looking the same. Okay, because if they're identical, it's easy, but if they are not identical, that's the hard part. So here, I read all of those images. I create a bag of features using this built-in command bag of features. I pass them all of the images in the data set. Here is the number of clusters that you want. I say only 50 clusters. So this parameter is your K that you have to choose. First, I read the first image of the data set. And by applying the method encode, which is for bag of features, I apply this bag of features to that first image and encode it. This way, I create the histogram of visual word occurrences, okay? This thing that I talked about for you. And then, once you know that, you can show it if you want. And then you are going to go over the query image, and you do that, and then you use a for loop, and you apply it now to all of the images you here, and then you do it, the bag of features, to all of the images. So you create your basically space, okay? And also, of course, this not only creates that, it also does the k-mean clustering in it. Then I do that for the query image, and now I compare the histogram for the query image against the histogram of the images in the data set, and that can be done here by this method called Jeffrey divergence, or if you want, you can use the toNorm. If you want, you can do that. From there, I find the best match, and I'm going to show it to you. Okay, in my next video, I'll talk more about Jeffrey divergence and comparing histogram against histogram. But if you want, you can use the L squared norm as well. Okay, so you're not bound to using any of them, but you can change this method here. You can change the number of clusters and anything else that you want. By the way, a few things that I need to mention is, one, the this method, first of all, you might say, what kind of feature detector and descriptor is this command bag of feature using in MATLAB? And the answer is surf. The descriptor is definitely surf. The detector is, I have to talk about it. There is a detector versus a grid. And I have to explain that. But first, let's look at the result. So this is the result. And it's very interesting. This is my query image. this is the best match that it found in the data set. And as you can see, actually, if you compare them, you see these two are the same location. But here you see the entire kind of, this pillar is there, here only a portion of it, but this Grand Hotel something sky is there, and it's there, and that kind of, those symbols that flag everything, okay? And these people are here, those people are not here. And you see that it actually did the job. And by the way, this is the histogram for visual words for one of the images. So if you wanted to see basically from these 50 different visual words or 50 clusters that we had, right? How many of them are present in the first image of the data set? This is the kind of thing that you have. And by the way, this is normalized histogram. This is not a histogram. The y-axis here is not frequency. It's frequency divided by max frequency, or some of the frequencies. This is a normalized one. That's why these numbers are all below 0.1. So this is kind of like a probability distribution. So it shows that, hey, this kind of features, whatever they are, these are the ones that are more frequent. This kind of features, whatever they are less frequent. Okay, so it shows you a histogram of those visual words for one of the images. And then you need to form the same histogram for each and every one of the images in the database, as well as your query image. And you actually, at the end, you're comparing histogram versus histogram. And that's why, instead of using the L-squared norm, I decided to use this method called Jeffrey divergence, which is a modified version of the Kullback-Libler divergence. It is better than that, and it is actually giving you the right answer. Now, let me just briefly mention what I wanted to say. So for detector, for what kind of salient point to pick, there are two options in here. One is detector. If you pick the option detector, then it is going to be the surf detector for picking the points. If not, then there is a default for it, and the default is called the grid. And what is grid? So here, basically, it breaks the image into a grid, and then basically from each cell in that grid, it picks one point as the salient point, which is not really the smartest way, because some portions of your image can have no prominent feature in them. They could be quite a bit uniform. But here is kind of trying to make that distribution of those points uniform, as opposed to let surf decide. So my option is always use the detector, not grid. Okay? The extraction, the descriptor for them, the feature extraction or descriptor, is always surf. Regardless of how you pick the points, the descriptor is the surf. And it typically, this method picks and keeps only the highest 80% of the strongest features. This 80% of the highest or the strongest features. If you want, you can change that. The default is 0.8. If you want, we can make it 0.5, 0.4, 0.6 to keep more of these features or less of them. And then for the clusters and for the vocabulary tree, you can provide two pieces of information. One is number of levels, the other one is branching factor. And here is how that space in the k-means clustering is broken down into different cells. Okay, you can either give it a single number, like just vocabulary size, okay, which is actually this guy, branching factor. And if you want, you can give it number of levels. So you can here break it into cells and let those cells be further broken down into smaller cells. Okay, so this is kind of treating it like a tree or a graph instead of that kind of picture that you expect from the k-means clustering. So if I want to show you this picture, I just took a picture of the book and show you, this is the kind of picture that you see in the book, our reference here. And this kind of shows that idea a little bit better. So you see that this is kind of that space that is determined by k-means clustering, and you can kind of see it like a graph and tree. So you can have the number of cells and how many branches can come off of them. Okay, so if you want, you can see it that way. So here I'm using only 50 of the cells, and I'm using the surf detector and descriptor. And then you see here it says that the number of levels here is the number of levels in the vocabulary tree. Branching factor is controlling the amount of vocabulary that can grow at successive levels in the tree. Okay, so these are some of the things that I wanted to explain for you, and you just saw the result. That was actually pretty good, correct? So let's just look at it one more time before we finish this video, right? So you see actually it did a relatively good job here. And if I want to show you these images, so these are these images, okay? These are these 200 images that I used. So you don't think that they are any similar or something, right? You can just click on them and just move on, right? And you can see that these images are actually quite a bit different from each other. And the fact that your system can actually, look here, detect which one of these places you were visiting, that could be relatively good. And it's mostly, again, here done with the surf. But you can use any other salient method and any other number of clusters. So this is kind of the picture that I was looking at. And you see I kind of trimmed it only to this region, and it did actually a relatively good job. So thank you so much for your attention. Stay tuned for my next video, which is going to be on global representation. So I'm going to use color histogram, and I'm going to use HOG finger prints, and so I'm going to introduce also the HOG for you, histogram of oriented gradients. Thank you so much. I'll see you in the next lecture.